This is Unit 6, Lesson 9, Correlation and Causation. Correlation does not imply causation. Even if two variables have a strong relationship or association, one does not necessarily cause the other. Causation indicates one event is the direct result of another. Just because there is a strong correlation between umbrella usage and car accidents doesn't mean that umbrellas cause accidents. The rain does. So it makes sense that, using umbrellas goes up and so does car accidents, but it's not because you're using the umbrellas that you're getting into car accidents. It's because there's rain and the roads are slick. Okay? Distinguishing association from causation. A strong correlation is not enough to prove causation, often because a hidden third factor is the real cause, like we just talked about with the umbrellas and car accidents. The actual cause is the rain, which isn't even a part of the scenario. Association is when two variables change together, okay, so like the umbrellas and the car accidents both change together, they're associated with each other. But causation is when one variable directly causes the other to change. Having an umbrella does not sorry, I'm tired. Does not cause us to get into a car accident unless you open the umbrella in the car. Okay? But rain can cause you to both carry an umbrella and get in a car accident. For example, there is an association between ice cream sales and shark attacks. The hidden third factor is hot weather. Hot weather causes more people to buy ice cream and more people to swim. The association is real, but the weather is the cause. The sharks aren't attacking you because you ate ice cream. They're not jumping out of the ocean and going and finding ice cream holding people. It's the hot weather that's causing both shark attacks and ice cream sales to go up. Okay. Here's example number 1. Consider this scenario. You are working at a snow cone stand one summer while your friend is working as a lifeguard near you at your local pool. Over the course of 1 week during the summer, you both decide to examine how many snow cone customers you encounter in a day versus how many people decide to go to the pool in a day. The data you both collect is shown in the table. So this is snow cone customers and this is pool goers. After examining the data, you both notice that more people appear to be at the pool on days when more customers buy snow cones. The data implies a positive correlation. When one goes up, the other one goes up too. Okay? At first, your friend insists that a reasonable conclusion is that when people buy a snow cone, they want to go to the pool. Could other variables influence why the number of snow cones sold and people at the pool may be higher on the same day? So is your friend right? Does buying a snow cone make you go, I'm going to go to the pool? Or could there be other factors at play? When you start to discuss other possible causes, you both realize that the snow cone customers were not usually the people going to the pool. You also realize that more people go to the pool than buy snow cones. You wonder whether there might be a more reasonable conclusion. You decide a third variable could be influencing the data, one you had not recorded, temperature. You also never considered how the day of the week could influence how many people had free time to buy snow cones or go to the pool. After considering these other factors, you both decide that although there is a correlation between snow cone customers and pool goers, the evidence is not sufficient to say that one of these causes the other. As previously stated, correlation does not imply causation. In this instance, you examined a scenario where there was a third unknown factor that influenced all of the data collected. So the correlation is not enough to assume that people buying snow cones directly causes people to go to the pool. Unknown factors influenced both the inputs and outputs of your data. The way I think about this is doing a scientific experiment. If you want to find out if something is causing like plants to grow faster, like if music causes plants to grow faster or taller or whatever, the only variable you change is the music. You would have like 2 sets of plants and one gets to hear music and the other doesn't, but they get the same amount of water, the same amount of light. Everything else is the same. In real world situations like this, people are not all the same. You don't have people that live the same lives, have the same jobs, have the same responsibilities, have the same amount of free time, have the same amount of income to decide when they're going to buy snow cones and go to the pool. There's too many variables for you to be able to say, yes, buying a snow cone makes you go to the pool. You can't run this scientifically, okay? Causation always implies correlation. So if I can say plants grow taller when they hear music, that's causation, and that means that they're correlated, that they are affecting each other, okay? Correlation does not always imply causation. So it works one way but not the other. You might think that X is causing Y. Snow cones are causing people to go to the pool. But it's possible that Y is causing X, that people are going to the pool because they bought snow cones. You have to look and say, can I flip this around? Could it be the other way? There also may be a third unknown factor at play, okay? So there's just two separate options that may make it so that correlation does not cause causation. Here's example number 2. Imagine that you decide to examine the income levels of friends, how much they make per hour at their part-time job, as compared to their self-reported happiness on a scale of 1 to 10, 1 being very unhappy and 10 being very happy. In your small study, you treat the income level as the input, X value, and the happiness level as the output, Y value. Okay? This small data set yields a positive correlation. As the input income level increases, the output happiness level also increases. You start to make the conclusion that income level must affect happiness, and that an increase in income must cause an increase in happiness. Is this conclusion valid? If you get paid more money, are you going to automatically be happier, no matter what? Well, if you stop and think about it, a common mistake when examining correlation and causation is assuming that X is causing Y when the opposite might be occurring. Maybe people are happier because they're making more money. In this case, we're working under the assumption that income was the cause and happiness was the effect. What if happy people are better workers who tend to be promoted in their jobs? Correlation does not imply causation for many reasons. You may assume that X, the predictor, is influencing or causing Y, the response. The reverse could also be true, where Y is influencing or causing X. However, reversing the predictor and response does not prove causation either. More research would need to be done before you could determine that a higher income causes happiness or that happiness causes an increase in income. The correlation of these variables does not indicate causation. Okay? You can't tell which one is causing the other if they are causing each other. For example, if you're paying me $500 an hour to babysit and your kid's a brat, I'm going to be a lot happier making $500 an hour than I am $5 an hour, right? For the same level of bratty kid. Correlation does not allow you to extrapolate. To extrapolate means to make big assumptions. So you're going beyond what the data says. We have the data and you're saying, well, this must apply beyond whatever we're looking at, okay? You cannot make predictions outside the domain of the data the same way that you cannot imply causation, at least not from a small scale and non-scientific study, okay? Again, if you want results that you can predict what else is going to happen or that are hard and fast results, you need to do it scientifically where you only have one variable that's changing between everything. If you're doing a really small batch, you can't say that this is a good example of what's going to happen because you might just have a whole bunch of similar people or a whole bunch of similar plants because you're only using 5 or 10 when you should be using 100 or 1,000. Okay. Here's example number 3. You decide to examine the number of hours your 5 best friends spend on homework as compared to their successes on the most recent math test. A quick examination of this data appears to show a positive correlation between the time spent on homework and the subsequent math test score. Overall, as the number of hours spent doing homework increased, the subsequent math test score also increased. The correlation is positive. If you were to study outside the domain of 6.5 hours, would you also earn a score of 100%? Can we say that? Can we extrapolate beyond this point and say, well, 6.5 hours got you 100%, so 7 hours will, 8 hours will? Can we say that? If you were to study outside the observed domain of up to 6.5 hours, it is not guaranteed that you would earn a score of 100%. Extrapolating beyond the range of the data can be unreliable because the relationship may not hold outside the observed values. I mean, look how small your sample size is. You've only got 5 people that you looked at. Other factors could influence test scores, and the trend might not continue indefinitely. If you study for 700 hours, you might burn yourself out and melt your brain and actually do really bad on the test. Another student may study for 8 hours and get a score of 80%. Maybe they studied the wrong information that wasn't on the test. Maybe they got burnout. Maybe they stressed themselves out. Maybe they just did really bad at studying. The small data set does not allow you to extrapolate to other data points. We cannot use this to go beyond this information. All we can use is this information. To show causation, you must rule out any other factors that might explain the relationship and demonstrate that one variable causes the change in the other. Ideally, this involves controlled experiments or studies where you can isolate the specific factor you believe is causing the effect. If, under these conditions, a change in one variable consistently results in a predictable change in the other, then you have stronger evidence of causation rather than just correlation. So again, you need to do a scientific study, you need to control stuff, and you need to repeat tests. I don't know why I have that there. So here's a check-in. Which of the following scenarios illustrate that correlation does not imply causation? Select the 3 correct answers. Smoking is correlated with lung cancer, and extensive research shows that smoking increases the risk of developing lung cancer. Those 2 things are both correlated and causated, okay? They show both because we know that through scientific testing. Vaccination is correlated with the reduction in the incidence of certain diseases, and controlled studies show that vaccination leads to lower disease rates. Again, scientific testing, controlled studies, this does show both correlation and causation. There is a correlation between shoe size and reading ability in children, but both increase with age. Obviously, we can't say kids with bigger feet are better readers. Those 2 things are not going to cause one another, right? They're correlated because in that data set they're correlated, but it doesn't mean that there's causation. There is a correlation between the number of people who use social media and the number of people who experience anxiety, but the correlation is coincidental and influenced by other factors. So this one straight up says that we can't trust the data. We know there's other factors influencing it, so that's not a good example of correlation and causation. There is a positive correlation between the number of coffee shops and bookstores in a city, but both increase with the city's population size. Well, yeah, everything's going to become more frequent when your population size grows. It doesn't matter if it's a coffee shop or a bookstore or a toilet or a cat or whatever. It doesn't matter. So this does not show correlation and causation. We're not getting more coffee shops because we're getting more bookstores. We're just getting more of everything. Okay. Here's question 1. Divorce rates in the state of Maine have a correlation with the amount of margarine people in the United States consume. Does this correlation imply that consuming margarine causes higher divorce rates in Maine? Okay, so do we have causation here? If you buy margarine, you're going to get divorced. No, this correlation does not imply that consuming margarine causes higher divorce rates in Maine. Correlation does not imply causation. The observed relationship between margarine consumption and divorce rates could be coincidental or influenced by other underlying factors. For example, maybe people are getting divorced because they're stressed about money and they're buying margarine because it's cheaper than real butter. That could be it, but it doesn't necessarily mean that that is for sure 100% it. Question number 2. If you have practiced the same number of hours a day as the best violin player in your orchestra practices every day, can you extrapolate to say that if you practice the same number of hours, you will become the best violin player in your orchestra? Explain. Can we say that? No, you cannot extrapolate to say that practicing the same number of hours as the best violin player in your orchestra will make you the best violin player. Practice is important, but it's not the only thing that makes someone a great violinist. Natural talent, high quality practice and instruction, and experience also contribute. Just matching the number of practice hours does not guarantee the same level of skill. It is important to consider the whole picture and recognize that correlation between practice hours and skill level does not imply direct causation. Again, there's too many factors at play, and you can't go beyond the data that you have. Guess what? There are no tests. That's it for this lesson. It's over.